Dear students, let us continue our lectures on machine learning for image processing. In the previous video lecture, we have discussed on the mathematical basics, highlighting the vector calculus aspects and as well as introducing the probability. So in this video lecture, let us continue our discussion on probability theory and random variables, focusing on joint random variables, marginal densities, conditional densities, and vector of random variables. Let me share the screen. Hope you are able to see the screen. In the previous video lecture, we have discussed about discrete random variables, especially introduced the notation of discrete that we use for discrete random variables. Also, we have considered an example to understand what discrete random variable is, and we mentioned that probability mass function is the one which will describe a discrete random variable, and it essentially gives the whole information about the discrete random variable. Similarly, we discussed upon the continuous random variable. There we mentioned that the probability density function plays a similar role as that of probability mass function, and it gives the entire description about the random variable, continuous random variable. Now let us see. Now let us continue our discussion on the discrete random variables. Let us see what the information that the probability mass function of a discrete random variable will give. So assume that x is a discrete random variable and x belongs to, say x can take one of the values from v1 to vm, and this is the set of values that x can take, be the set x or set v. And in an event, the x can take any of these values, and probability which the x can take either of these values is given by probability that x equal to vi is equal to pi. Okay, and essentially giving all pi for all I is what is meant by p of x, or the probability mass function. Okay, so that we will be getting the information of probability that x can take, this random variable x can take any of these values. That's what is referred to as probability mass function, and or explicitly which is given as here. Okay, now let us see what information does this probability mass function give. As discussed in the last class, probability mass function or probability density function are the complete descriptions of a random variable. Okay, so with this, say for example, consider the same example that we have considered in the last class. Let x be in like the random variable. X is decided based on an event of throwing a die. Okay, so it's like okay, so in this case, it can take any of the values. This vi's can be anyone from, okay, so I will write directly the set of vi or x now, which the new notation that we have introduced, 1, 2, and up to 6. It can take any of these values. And with what probability if the die is unbiased, then each of the probability that x takes any of the values vi, okay, for I equal to 1 to 6, okay, which is pi is equal to what? It is 1 by 6. And hence, pictorially, if you would like to show, what we show is, okay, it is 1 by 6, 1 by 6, 1 by 6, and so on, 1, 2, 3, 4, 5, 6 for all the events. Possible outcomes that we can get. Okay, for the random variable x, and this height is 1 by 6. Okay, so now see, by visually looking at it, we can know that the random variable is uniform random variable, and probability probability mass function P of X clearly indicates it. Okay. Now further, if you want to find the mean value that the outcome can take in this experiment, or the random variable can take in this experiment, what we get, what we refer to as expected value of the event X. Okay. So expected value of X is written as, so it is, how do we define it? P of X into, okay, X into P of X, where X can take any of the values in the set X. Okay, now among all its possible values, this can be explicitly written in this case, I equal to 1 to 6 Vi into P of Vi, or what do we, how did we define this? So this is in fact whatever we have defined is P of Vi. Okay, so how do we how can we write this now? I equal to 1 to 6 Vi into Pi. Okay, which is equal to what here? It's equal to, you can calculate, and it will be 3.5. Okay, this is the expected value or mean value that X will take among its possible outcomes. Okay, so this mean value gives more or less around which the other possibilities of the outcome will be. Okay, now see, you can see here mean value is located here. So the mean value is exactly the here as you can see at the center. Now, as I said, mean value gives a indication or quantification how the other possibilities of the events that can occur. See, what are the possibilities in this experiment that can occur? So VI can take a value 1, 2, and so on up to 6. So you see, the mean value is reflectance of it. Okay, it's 3.5 indicates that half of the possibilities are this side, half of the possibilities are that side, since this is a uniform, okay, random variable. Okay, so this example we have considered in after this throwing die event is what we essentially are using, like what we get is uniform distribution. Okay, so now see, not necessarily the mean, we can also find any of the movements of the random variable, okay, that are function of the random variable. Fine. So like the expand, how do we find f of X into P of X? That's how we find the expectation of any function of the random variable, where X is from, again, from the set of all possibilities it can take. This can also be written f of Vi in this case into Pi. I have directly written here. Okay, I varying from 1 to 6. Okay, so now one specific function of this X is very important. See, as I said, the mean value indicates, okay, mu equal to 3.5 indicate value of outcome, value around which the all possible outcomes are centered. Okay, so indicate a center value around which all possible outcomes are happen. Okay, all possible outcomes happen. Let me just write this. Value around which all possible outcomes happen, I will write, occur. Okay, so now see, when all possible outcomes are around this, it is not necessarily that they can be equally around this. Okay, in some situations or in some cases, if possible outcomes can be more, say for example, if I have the values Vi is equal to slightly the different possibilities are say 1, 2, and then say for example there is a die which has, okay, on the top of it 1, 2, and then again immediately starts from, okay, 6, 7, 8, 9. Okay, so in that case, the center may be more towards this 6. Okay, so like that. So in such case, there may not be equally distributed number of possibilities in both sides. Okay, so the spread around around the mean value where the outcomes occur is also of great interest. Okay, so that is quantified by using a function called expectation of a function called x minus mu whole square. Okay, expectation of x minus mu whole square gives that the spread of the possibilities around the mean value, and this is referred to as variance. Okay, and this is referred to as mean of random variable, and this is referred to as variance of random variable. Okay, and here as you can see, this can be computed based on the previous formula I gave or the discussion we had into p of x, where x belongs to all possibilities of outcomes, any of the possibilities of outcomes. This can also be written in with the notation that we have as what? Vi minus mu whole square p of xi or directly pi. Okay, in this example. Okay, in general also you can write among all the possibilities, I varying from 1 to m possibilities. Okay, right. So this gives the spread. As you can see in the case 1, so let us see, calculate the mean value even here. So you're assuming uniform probabilities. Okay, mean value in this example, okay, mean will be 1 plus 2 plus 6 plus 7 plus 8 plus 9 by what? By 6. There are 6 possibilities. Okay, you can see that actually it is 10 plus 10 plus 13. Okay, so it is 10 plus 10 plus 13, 33 by 6, and this is 11 by 2, and this is equal to 5.5. See, in this case, you can see that the mean value is, okay, mean value has moved towards 6. And then the number of samples, number of outcomes, okay, on the either side of mean value are not same. Okay, they are high on another side and maybe less on another side. Okay, now if we see the spread variance or this spread around the mean value or the variance around the mean value in both experiments, say assume that this is case 1, okay, where we have the die having like 1 to 6 on its faces. Okay, and this is case 2. This is case 2. Okay, so can you tell, say the variance, can you compare the variance in case 1 versus case 2? Sigma square and sigma 2 square. Which do you think will be higher and which do you think will be smaller? Okay, the answer is sigma 2 square will be higher, the spread, because as you can see, the samples, the mean is at 5.5 and the samples go from 1 to 10 roughly. Okay, so they span over 10 like 10 values, 10 units. Okay, even spread around the mean value is, okay, roughly 5.5. Okay, roughly 5 at least. Okay, on 5 on this side, 5 on this side. Okay, mean the spread around mean value in the case 1 is around 3. Okay, so the variance in the second case is higher. I request or suggest you to compute the variance explicitly in case 1 and case 2 and verify this. A simple information that is intuitively seen here. Okay, so now let's move on. This is these movements, that is mu and sigma square, okay, are very important. These referred to as movements of random variable. Okay, so and they are very important characterization of a random variable. Okay, it's not easy to get the information about the probability density function or p of x of a random variable. Okay, however, computing mu and sigma square of a random variable are fairly easier. Even for that reasons, people take these as the good information, piece of information to understand the outcomes of a event, okay, or the random variable. See, in our examples, say assume that I have some, let us go back to the situation where we have uh, mm, the classification problem of two kinds of fishes and we are measuring the lengths. Okay, assume that I have a class 1 samples, okay, and I measured lengths of a class 1 samples, L1, L2 and so on. Assume that there are 100 samples. Similarly, now I have class 2 samples, okay, I let there be class 2 samples. I again has measured the lengths of these samples, L101, L102 up to, say for example, another say some samples L250. Okay, so I have more samples for class 2, assume that. So now given this information, what may be interested is, see, if I ask you to find p of x, the probability mass function of class 1 samples and probability mass function of class 2 samples. Okay, so do you have any idea on how do I find it? Just think of. Okay, so if you have an idea of finding probability mass functions of class 1 and class 2 samples, measuring their lengths, see, one more thing that is to be considered here is the length is a continuous random variable. Okay, so this is a continuous random variable. And hence, what will you get when you find out the probabilities? How do you characterize this continuous random variable x? Is by using probability density function. Okay, and hence the discussion now is on the probability density function, okay, rather than on the probability mass function. However, the computation of the whole like movements and all the discussions that I mentioned with the discrete random variable are equally applicable for continuous random variable. Please make a note of it. Okay, so except that, so can one of you guess what will happen if you want to find the mean of a continuous random variable? The summation will become the integration, that's all. Okay, this is again expectation of x, okay, is equal to mean value, which is equal to whatever I am writing here. This goes from minus infinity to infinity, and p of x will give, okay, p of x given. Okay, then what we do is to find out the mean of a random variable. And then the variance, how do I find the variance of a random variable? Minus infinity to infinity, x minus mu whole square into p of x dx. Okay, summations becomes integrals. That's only the difference that we have. Okay, so given this scenario now, the question is, okay, so even if I find the probability mass functions or probability density functions, okay, so in these situations, do you think can you characterize them by a nice probability mass functions of this sort? See, as I said, this kind of mass function where all the events are of have the same probability is referred to as uniform distribution. Okay, in the previous class I introduced about the Gaussian distribution, where there is a peak at the center or the mean value, and then they die down on both sides. Okay, and mathematically this probability mass function for a Gaussian probability mass function, okay, you can write it as 1 by root 2 pi sigma e power minus x minus mu whole square by sigma square. Okay, where sigma is the spread around the mean value and mu is the mean value. And this is the mathematical function that guides us to sketch this probability density function and the random variable x following this frequency plot. Okay, on y-axis for the possible outcomes in the x-axis is referred to as Gaussian distribution. Okay, so Gaussian density here because it's a continuous random variable. Now the discussion here is, even if I measure the lengths of 100 fishes of class 1, lengths of 100 to 150 fishes of class 2, then if I find out the probability mass function or the probability density function, okay, they may or may not follow any specific shapes that we know or any specific distributions that we know. Okay, so in such cases, it is not easy to model them. So rather, finding out the information like mu1 and sigma 1 square, okay, or mu2 and sigma 2 square for class 1 and class 2 samples will be fairly easy. And good enough, maybe good enough to design particular classifiers. Okay, so for that reason, finding out movements plays an important role for random variables. However, if we can find out the density function or the mass function, it's more than much more information, and it can be done only in particular cases. Okay, so now let's move on and now discuss on the joint random variables, joint densities of more than one random variable. So let us consider now, let x and y be two discrete random variables. Okay, and these discrete random variables, x can take any of the value from capital X, set x. Okay, that may have any some possible values, and y can take any of the values from capital Y. Okay, so x and y are sets. Possible outcomes for x random variables x and y. Okay, so now in this case, if I want to understand or get the whole information about these random variables, it is not good enough to get p of x. Since we are discussing about the discrete random variables, I am writing as p of x. Okay, that is probability mass function of x or probability mass function of y, that is p of y, are not complete descriptors. Okay, when we want to know the whole information about two possible random variables involved in an experiment where both of the random variables can take any of the values, we should know not just the information about a random variable x alone or y alone, since there are in the event both random variables are possible. Okay, so there is a information that jointly need to be understood, or the effect of one on the other, or the influence of influence or not being influenced by one random variable on the other has also to be understood. So that whole information now can be captured by joint probability mass function Same things occur for continuous random variable as joint probability density functions. P of x comma y. Okay. So now this gives the whole information about the random variables x and y. So now the same properties, okay, that we have for the random variable also occur for this. Is greater than or equal to 0, and then summation of, okay, all possible outcomes, okay, from x, y from y, okay, for all the possible, say, having the is equal to 1. P of x comma y essentially indicates what? The probability that, okay, or let me write in small notation, probability that, okay, x take a particular value is equal to vi. Assume that from set x, and y takes a particular value ui from again set x. Okay, so this can be written as ui comma vi as well. Okay, so taking a particular event, the probability that x take a particular event of x equal to vi and y equal to vi is what is the joint probability. Okay, a mass function here. Okay, and that gives the information about this. And probability mass function gives for all the possibilities. Okay. Okay. So now with this, what more additional information do we get is, okay, so see, we can find out P of x given x, that is marginal density of x. If I want to understand how the random variable x alone behaves, what I do, I sum all the like the probability that for a given x random variable, x takes a value xi. Okay. All the possibilities of y. I think we'll write x can take, random variable can take any value in the set vi. So for a given x equal to vi, okay, what we do, if we sum all the possibilities of the probabilities, okay, that P of x equal to vi comma y, what you get is a marginal probability, that is P of vi I am writing. Okay, as per our previous notation, which is pi, which we had before. Okay, so similarly, if you want to write the information or the marginal density, this is referred to as marginal density. Here mass function, distribution, marginal distribution function. Okay, P of y, if you want to write, how do we write? Now sum across all the possibilities and their probabilities, okay, for a given value of y. Okay, so it's here y is fixed. So we can say that probability that, say, y may take a particular value ui. Okay, for that qi, let this be qi, probability of ui is equal to x belongs to all possibilities of x, probability that x comma y takes the value of ui. Okay, so same things occur in the continuous random variables as well, with the summations being replaced by the integrals. Okay, so once the joint probability mass function is given, we have the whole information about, okay, the co-occurrence of random variables x and y as well, or the individual occurrence of the probabilities of individual occurrence of random variables x and y. Okay, so the whole information is with us. Okay, in case if this information is given, right? Okay, so what additional information do we think we get when we are given the joint distribution or joint density function? Is that, see, I may get the, say I may want to find out the joint moments now. So assume that, say I want to find the mean of the random variable x when we have the joint density, that is p of x comma y. What do we do? So usually that is what is expected to be found is the expected value of x random variable x is what we want to find. And how do we find this? Now when we are given joint distribution, it is x into p of x comma y, and summation now goes over x belongs to x. Okay, same in the similar way that we were doing before can be done now, except that the summation corresponds to corresponding variable on which we want to find out the moment. Okay, so similarly now let us continue to find e of, so x minus mu whole square. If you want to find sigma x square, which is equal to x belongs to x minus mu whole square into p of x comma y. Okay. Here, in addition to the discussion we had, we should also bring in the double summation, because for all the possibilities of y, okay, we will see the movement of x. Okay, so because even though we want to find out the expectation of x, what we have is joint probability mass function or joint density function. Okay, to get the marginal in some sense, see, because this summation is independent of x, to get the marginal, we need the first summation, and the second summation is to get the expectation. Okay, please note that. So you need now double summation, wherein the first summation is for getting the marginal corresponding to p of x, and then second summation is this. Okay. One more aspect to note is that it's not always the case. If we have p of x comma y, okay, we can write p of x, okay, that is the marginal density, and p of y, okay, just as like separately from p of x comma y. Okay, both may be dependent on each other. When we consider joint like distributions, x and y may or may not be independent. Okay, so what do we mean by independent? They're independent if and only if, okay, if p of x comma y is equal to p of x into p of y. Okay, so only if the random variables x and y are independent, okay, then we can separately write p of x and p of y, and we can compute the joint density itself. Say if I give you marginal densities, okay, I can find out the joint density p of x comma y. Otherwise, the co-occurrence makes them more complex, and you cannot break them into individual or you cannot find out the joint density from p of x and p of y. Okay, you can find out p of x comma y from p of x and p of y only if x comma y are, okay, independent random variables. Otherwise, you will not be able to find. Okay, so what is this new term independent random variables? Let me give an example here to understand this better. Let's say you have you are parallelly conducting two events. One event is throwing a die, and other event is tossing a coin. So event 1 is tossing a coin. Okay, event 2 is throwing a die. See, what are all the possible outcomes here? Here, Vi is equal to 1, 2. Only two possible outcomes. Here, possible outcomes are, okay, 1, 2, and up to 6. Okay, and both are unbiased, assume that. So you can calculate all the necessary things for that exam, for these events. Now, in this case, see, I said both, like I'm doing this with one hand, I may be doing this with other hand or whatever. So I'm doing this one time, I'm doing this other time. Now, what can you tell about the nature of these two events? These two events are now independent. Okay, so I am conducting both of them together, but one has no dependence on the other. Okay, the value of value Vi, okay, that is outcome in event 1 has no dependency on value Ui, that is outcome in E2. Okay, you can get 2 and 6. You can get 1 in first event and then 1. Okay, it can be anything. This is case 1. Can you construct a case where there are dependent random variables? Example of, okay, dependent random variables. See, what I can say is, I will see, let us consider a real example. The number of students coming to the class, okay, is, let that be the time of a student coming to the class, or the number of students coming to the class at a particular time. Let that be a random variable. Okay, so I have, say, for example, assume that we have class at 9. Okay, the number of students coming to the class at a given, like around 9, is a random variable. Now, the faculty coming to the class is another random variable. Okay, so if it is known that the faculty usually comes late, okay, then what will happen? The number of students that come at 9 also will be relatively lesser. Okay, or if the faculty comes even little early or whatever, okay, the students will be sharp on 9. So it depends upon, this is an example of dependent random variables. The number of students coming to class, okay, at 9. Okay, let this be event 1. The number of students coming to the class, and event 2 be the time at which faculty come to class. Okay, so here also the number of students will become probability. The time at which students come to the class is the random variable. Is a random variable. The time at which students coming to the class, the time at which faculty coming to the class. Okay, these two are like a dependent example of a dependent random variable. Okay, as you can easily understand. Now, similarly, you can also form with event C2 that we have discussed in case 1, a dependent random variable. Say I will throw die, okay, till I get 2. If I get the if I get a 2 in the coin tossing experiments, then the event 2 I will say as the number of times I throw the second die. Okay, so and then the I will throw the die till I get 1 if I get 1 in the first experiment. So that is coin, when I coin gives 1, and the coin is a biased coin. Okay, then what will happen? It depends upon the first coin. The coin itself will influence how many times I have to throw the die. Okay, so that's an example of a dependent random variables, and a joint density where you have dependent random variables. Okay, so if the coin is biased, and then I will throw the die based on the, even say for example, the number of times that I get 2, or the number of times that I get 1 in when I throw the coin for 10 times. Okay, then it's and the event I note as the value of die that it gives as second event, and the first event is just throwing the coin for 10 times and noting how many times the head and tail comes. Okay, so that's a dependent random variable. Okay, please note I have written 1 and 2 here, but you can replace this by head and tail as well. Okay, right. So now a little bit more discussion around this. You can compute here when you have two random variables, not just the movements of a single random variable x or y. Okay, similarly, as we have discussed here, you can also find out expectation of y, okay, and expectation of y minus uy whole square, or where ey is the expectation of y is referred to as uy. Right? Similar to this, you can also compute the expectation of joint densities x minus mu y into y minus mu y. Sorry, x minus mu x into y minus mu y. Okay, so this is referred to as covariance of random variables x comma y. Okay, we will see this in the next slide with a little more discussion. So when we have x, y are joint random variable or random variables, okay, and p of x comma y denote joint probability mass function. Okay, expectation of x minus mu x, y minus mu y. How do you think is this defined? It is defined as x belongs to all possibilities of x, y belongs to all possibilities of y. Okay, and then x into, because the expectation happens on both. Okay, sorry, we should bring in whatever is the function that's here, mu x here, into p of x comma y. Okay, here probability mass function of x comma y. Okay, so this is how we find the joint expectation. So this is how we find the expectation of x minus this is the joint spread or the correlate. This is also referred to as covariance, as I said. Okay, what information does this covariance gives is, see if there is a increase in x, will x also be increasing, y also be increasing, or vice versa, or is there an effect of x variation on y? Okay, that information is explicitly given by this term, covariance. Okay, further a small discussion around this, we can consider this as a, since expectation is a linear operator. See, please see here, it's all done with summations, okay, or integrals. So integrals or the summations are linear operations. So what you can do is you can multiply inside. And then you can apply expectation across each of the terms. See, since as I said, expectation is a linear operator. Any linear operator when we apply, say for example, linear operator means say f of a comma x. If f is a nonlinear function, I can't take out a. But if f is a linear function, okay, f linear means a into f of x I can write. Okay, similarly, f of x1, ax1 plus by1 or ax comma by. If the function is linear, what can I write? A into f of x plus b into f of y for a linear function. Okay, yes. So that's what I am using here. Okay, I have applied the same function expectation to all the terms or components here. I'm applying it now. Further, what can I do now? What may be my next step to simplify this? See, expectation of a constant is what? Expectation is defined only when there are probabilities. Okay, if there is no probability, there is no expectation that need to be defined. It's itself is a constant. Okay, so the mean value of constant is same constant. So what you get now is simply this term is nothing but, okay, what you get here is mu x and mu y. Okay, and what is this term? This term is nothing but, see, you can take mu y out. Okay, and then expectation of x, because x is only a random variable here. Okay, here similarly, but here both are random variable, you have to retain this. And similarly here, what you will get? Mu x out and expectation of y. What is expectation of y and expectation of x? They are mu x and mu y. So this gets simplified as, so this is expectation of this covariance. Oh, we can, as I said, we can also write this as covariance of x comma y, random variables x comma y. Okay, so now covariance of x comma y, you can write this as, okay, these are actually no, this is off the discussion. Okay, so here, if we continue here, expectation of xy minus, say, mu x into mu y into mu x. So 2 times mu x mu y plus 1 times minus 2 times mu x mu y plus 1 times mu x mu y. So the effect to simplify, it simplifies as this. Okay, so here this is the covariance term. So it can also be written in general, expectation of y, xy minus expectation of x into expectation of y. Okay, so for a, if the random variables are uncorrelated, okay, that means, see, if there is no influence of x on y and y on x, then what we can say is covariance is equal to 0. Uncorrelated random variables. That means, see, we are not directly writing the joint density or joint mass function as the marginal mass form, product of marginal mass functions. However, we are saying that there is no dependence of x on y explicitly here. Okay, still, for computing the marginal densities, you may need the information of x on y. Okay, So for an uncorrelated random variable, what we say is covariance xy equal to 0. That means expectation of xy, that what does it imply? This implies that this is equal to 0. Okay, that implies expectation of xy is equal to expectation of x into expectation of y. That means the mean of random variables, joint mean of random variables can be found by product of individual means. Only up to that we can assess or confirm, okay, if the random variable is random variables are uncorrelated. Okay, so whereas if the random variables are independent, you can directly write these as the product of the marginal densities itself. Okay, so what we can infer in uncorrelated case is the means of the experiment 1 and mean of the, see, if I conduct experiments here, throwing say coin and throwing a die. Okay, so I design the experiment such that the say I will give value 1 to this and value 2 this. Okay, 2 to this for computing the means and so on. Okay, on the head and tail of the coin. Okay, then I may the I design such that the event 1 is always has a mean of 0.5, like in between 1 and 2. The throwing die always has a mean of 3.5. However, one experiment like throwing a die may be dependent upon throwing a coin. Okay, so both are dependent events, but the event is only throwing a coin or throwing a die. So what may happen in when I conduct event E1, the mean is 0.5. Okay, and the when I conduct event E2, mean is 3.5. However, I will make them dependent, saying that okay, when I get 2 here, I will throw this. Okay, something like that. Okay, so in that case, the probability like you can compute the joint expectation simply based on the multiplication of the expectations of two different events. Okay, but however, you cannot comment on the joint density, okay, directly uh, without knowing further information about the experiment and the probability, joint probability mass functions. Let me see if I can give you a better examples for the where the cases for the cases where the uncorrelated random variables and independent random variables can be distinguished. However, these two are important concepts in understanding the nature of random variables, and most of the times we assume the random variables are uncorrelated or even strictly they're independent. Let us now discuss on the vector of random variables. With that, we will conclude this video lecture. Now assume that the random variable x, okay, let I have a vector of random variables x1, x2 and so on up to xd. All x1, okay, x2, xd are random variables. Okay, so in this case, here what we have is a vector of random variables. Can you give an example where this may happen? If I have class 1 samples and class 2 samples, now assume that the same fish example, I will be measuring length and width here. Okay, and then light and then intensity. Okay, for each of the fishes. Oh, these three together will become my random variable, length, width and intensity. Okay, so that will be measuring for 1 to 100 samples here. Okay, and then I will be measuring from 101 to Okay, 250 samples of class 2. Okay, so now I have a vector of random variables. Okay, so now in this case, exactly whatever the discussions we had on the joint densities and joint distributions also follow. And so we can write now P of x is equal to, see, it depends upon not just one feature or the one element or one random variable. It depends upon all the random variables. This is now the joint density, joint mass function of random variables. Okay, x1 to xt. Now, with this, see, assume that if I give a condition that, okay, x1, x2, up to xd are independent random variables. Okay, if these are all independent random variables, then what can you comment about this now? We can say that, how can we write P of x? Joint density P of x. So please note that I'm writing capital X for the vector, or all random variables put together, I'm writing capital X. Okay, is equal to, if they are independent, then what we discussed, the joint density is product of marginal densities. Okay, so this is the like great advantage if we know that the random variables are independent. Finding out marginal densities are very simple. In an experiment, when I can measure the fish length, I can take the only length alone and then make this measurement P of x1. Okay, so whereas if I want to measure the joint density, what should I do? I should measure length, okay, width and intensity for all the fishes, and then the joint density will be a histogram. So for example, for a single feature length, okay, if I just want to measure the density or marginal density, what I do, I measure length for all 100 fishes. Okay, and then for different values of length, I will plot the histogram. Okay, so this will give me P of L or P of x1. Okay, so that's how I measure, I get in real situations the marginal densities. Okay, x1 equal to L, and this is P of x1, how I got. It may vary from several, if this is 0 0 to 10 or whatever, it may vary. Okay, so I have measured lengths up to, in a bin I have counted how many number of frequency of fishes of C1 class 1. Okay, I in say around 2 to 3, how many fishes are there? With the length between 2 to 3, how many fishes are there? That's what is the number here. Okay, between the fishes in 3 to 4, the number is here. Okay, 4 to 5, number is here, and so on. So that's how I quantify, assume that. Okay, and got a probability mass function for discrete bins of length L. Okay, so I have a probability mass function, or I considered L as a discrete random variable, considering 2 to 3 as a single bin. Okay, that's how I got the probability mass function for a single feature X. Whereas now, if I want to make a probability joint probability mass function for all the three, then how do you think will it look like? It look like in 3 dimensions. Okay, I have to sketch this in 3 dimensions. Okay, this is being x1, x2, and x3. Okay, and on the I will be having a 3-dimensional histogram to understand how the joint distribution varies. Okay, and they may be joint distribution, maybe one length also may be dependent on width when I measure for class 1 samples. Okay, and the sample even intensities may be dependent upon that class. Okay, so they may or may not be independent. However, if I make the assumption that length is independent of width and width is independent of intensity for the class 1 samples and class 2 samples, then I can make this simplification, and each of the densities can be marginally measured by using histograms. Okay, so another aspect here, so if I assume that now if I want to find out the expectation of this vector x. I just want to find out expectation of this vector x. How do I find out? Then expectation of the random variable 1, expectation of random variable 2. See here, when I find out expectation of particular random variable, what I'm using is, I'm using the formula like I have given before. If I have only joint distribution, or if I have a marginal distribution, then I can directly use that PMF alone corresponding to that variable. And this is referred to as mu x. Okay. So there is one important additional discussion that we should have when we consider a vector of random variables. That is covariance matrix. What will happen to covariance? Okay, in this case, for a vector of random variables, expectation of x minus, assume that I have got x minus mu, sorry, this I write as x minus mu. This is a vector. Please note that now mean vector. Okay, this can be written as mu1, mu2, and so on mu d. Okay, where mu1 is expectation of x1, mu2 is expectation of x2. Okay, so now x minus mu transpose. So rather than getting a single covariance value, previously whichever I denoted as sigma xy, okay, see here what covariance of x comma y we usually denote with, okay, sigma xy. Okay, so instead of this, what we are getting here, this is what is x sigma xy. Okay, covariance of x and y. Instead of this, what we get here, the overall covariance is, see, x1 may vary with x2 or with xd or with any other component like random variable x in different proportions. Okay, so what you may have here, what you need to define here is a covariance matrix. Rather than to define it as a covariance. Please note that. Now, if I expand this, how does it look like? Expectation of x1 minus mu1. Okay, I am just writing x and mu vectors explicitly into. So please note that this I will write explicitly to expand it better. So x1 minus mu1, x2 minus mu2, and so on, xd minus mu d. Did you people have seen this kind of vector multiplication anytime? And did we define it with some value or with some term? Expectation of this I am doing. x1 minus mu1 transpose I am writing, x2 minus mu2, xd minus mu d. What did we define for a vector multiplying with its transpose like this? What did we call it as? This is referred to as covariance matrix of x comma y. Okay. What did we call this as? We have called this as outer product of two vectors. Okay, of a vector. Outer product of a vector is written like this. Okay, so expectation of, so I will write expectation, since being a linear operator, I will bring it inside. Expectation of x1 minus mu1 whole square. Okay, expectation of x1 minus mu1 into x2 minus mu2. Okay, and so on. Expectation of x1 minus mu1 into xd minus mu d. Okay, please note that. Okay, similarly now, so here expectation of x2 minus mu2 whole square will be here. Okay, and here expectation of x2 minus mu2 into x1 minus mu1. Okay, so on, so on. I'm not writing all the terms. Finally, what you get here, expectation of xd minus mu d into x1 minus mu1, and finally here xd minus mu d whole square. Okay, so this is referred to as covariance matrix of random vector or vector of random variables x. So here covariance matrix, right? I said, sorry. Vector X. Okay, so X itself has all the components here. Please note this. Okay, so and if we explicitly write this for 2 dimensions, how does this look like for 2 dimensions? So let me write with this color just to have the. Okay, with this, when we write this for 2 dimensions, say assume that X only has X1, X2. Okay, and then in that case, expectation of X is expectation of X1 and expectation of X2, which is mu1 and mu2, and this is the mean vector. Okay, and then the covariance of X is written as expectation of X minus mu into X minus mu transpose, which is equal to expectation of X1 minus mu1 whole square. I'm just directly writing the answer. Expectation of X1 minus mu1 into X2 minus mu2. Have you seen this? Expectation of X2 minus mu2 into X1 minus mu1 and expectation of X2 minus mu2 whole square. So how do I write it? I just want to write a shorthand notation here. Expectation of what is the first term called? Sigma 1 square. Variance of first random variable, sigma 1 2, sigma 2 1, and sigma 2 square. Okay, so please note that sigma 1 2 is covariance of first with another. Sigma 2 1 is covariance of second random variable with first random variable. Okay, expectation of X1 minus mu1 into X2 minus mu2. Most of the cases they are same, but in some cases they can differ as well. Okay, it depends upon the joint density function. Okay, whether they differ or not. Fine. So now, right. So let us assume that this joint density function is symmetric or roughly same. So if they are independent, it is then what will happen? As a particular special case, if we assume that the joint density function, okay, P of x1 comma x2 is equal to, if they are independent, P of x into P of y, x1 into P of x2. Also, you know that covariance x1 comma x2 is equal to 0. Okay, if they are independent, in such case, sigma 1 2 is equal to 0. Sigma 2 for independent or uncorrelated. X1 comma x2. In other cases, you will have finite sigma 1 2, and there is usually a term that is defined as correlation coefficient. This term indicates how much dependent, okay, interdependent this features x1 x2 are, or the random variables x1 x2 are. Okay, it is defined as sigma 1 2 by sigma 1 into sigma 2. Okay, so ideally if they are not dependent on each other, one doesn't vary with the other, then sigma 1 2 is 0. Or if x1 is increasing, x2 is also increasing, random variable, assume that in an experiment, then what may happen? They have a positive correlation, positively correlated. Okay, and if say x1 is increasing, x2 is decreasing, then they are negatively correlated. So the range of this varies from -1 to 1. This sigma 1 2 is always less than, okay, sigma 1 into sigma 2 from based on some inequality, Cauchy inequality. Okay, there is a inequality that says that sigma 1 2 is always less than sigma 1 into sigma 2. Okay, and then correlation factor, correlation coefficient always lie between, thus it lies between -1 to 1. +1 means they're positively correlated, -1 means it is negatively correlated, 0 means no, not correlated. Okay, And this is usually defined as the covariance matrix. This completely describes about the spread of the random variables x1 and x2 within each other and between each other. Whereas the mean value indicates the mean possible outcomes of x1 and x2. With this, we will conclude this video lecture. In the next video lecture, we will discuss on the, in the next lecture, we discuss on the Gaussian distribution and its some of the properties of Gaussian distribution. With that, the math discussion will be complete and we will move on to the discussion on Bayesian classification. Thank you.